In another screencast, I introduced all the properties of vectors, so you need to watch that first before you see this one, and that one was called Vectors in the Plane. In this screencast, we're going to talk about a special way you can multiply vectors together called the dot product. And what it says is that the dot product of vector u and v is the product of the x components plus the product of the y components. And you're going to get out not another vector, you're going to get out a scalar. Okay, now here's some properties of the dot product. It's commutative, which means the order doesn't matter. 0 times 0 dot any vector is 0. You can distribute the dot product, and v dot v, a vector dotted on itself, is equal to the magnitude of the vector squared. And you can also do the scalar times the first vector and then dot the second one, or do the scalar times the second vector and dot that. Okay, let's do some examples. Let's find the dot products here. So if I have this vector 6, 4 and this vector -2, 3, then that dot product is going to be 6 times -2 plus 4 times 3. And that's going to equal -12 plus 12, which is 0. Okay, so notice that I did not get a new vector. I got a scalar, just a single number, just a magnitude out when I do the dot product. Okay, so now I have three vectors. Vector u is -2, 4, vector v is 1, 3, and vector w is 3, 5. We need to find u dot v times vector w. All right, let's get u dot v first. Okay, so vector u dot vector v is going to be -2 times 1 plus 4 times 3, which gives us 10. And then I'm going to multiply that scalar times vector w. And I get 30, 50. Okay, so the dot product also helps us find the angle that is between two vectors. Okay, so if I have a vector u that's going 4, 3. So let's see, 1, 2, 3, 4, 1, 2, 3. So here's vector u. And then I have a vector v that's going 3, 5. Okay. So here's vector v. Then here's the angle theta between them. Well, we can get that angle theta by using this formula right here. Okay? So let's just work it out. The cosine of theta is going to be 4 times 3 plus 3 times 5 on top. That's the dot product of u dot v. And then the magnitude of vector u, remember, is the square root of 4 squared plus 3 squared. So that's 16 plus 9. And then the magnitude of vector v is 3 squared plus 5 squared. Okay, so that's 12 plus 15. That's 27. The square root of 16 plus 9 is the square root of 25, which is 5. And then that's the square root of 34. Okay, so the cosine of this angle is equal to that ratio. Let's get our calculator up. And I'm going to go second cosine 27 divided by parentheses 5 times the square root of 34, close parentheses. Well, let's delete that. Let's arrow out from underneath the square root. There we go. Close parentheses, and then close parentheses for the inverse cosine. And in degree mode, that's 22.17 degrees. So theta is equal to 22.17 degrees. That's the angle between vector u and vector v. Okay, so here's a weird word, orthogonal. What that means is if I do the dot product of two vectors and I get the answer is 0, that means u and v are orthogonal, which means they are perpendicular to each other. Okay, so if vector u dot v ends up being 0, that means there's a 90-degree angle between them. Okay, so now let's talk about vector components. Let's let vector u and vector v be non-zero vectors such that vector u is vector w1 plus w2. So here's vector u, and its horizontal component is w1, and its vertical component is w2. And if I add those two vectors together, I get vector u. Okay, they're orthogonal. They're 90 degrees between them. Now, vectors w1 and w2 are called vector components of u. And the vector w1, this vector right here, is the projection of u onto v. Now, v is this vector right here. Okay? I kind of wrote over it, but there's vector v. And w1 is the projection of u onto v. If it helps, you can think of w1 as kind of like a shadow. And if vector v is going along the horizontal, I shined a light down on top of vector u, its shadow would be right over on top of vector v. Okay? So w1 is called the projection of u onto v. And we get vector w2 by just taking vector u and subtracting w1. Because up here, if I subtract w1 from both sides, I get w2 equals vector u minus w1. Well, what if v isn't horizontal like in the previous example I showed? What if I've got vector v like that and vector u like that? Okay, well, the projection of u onto v is given by u dot v over the magnitude of v squared times vector v. And what that looks like is this vector right here that I go out to, such that that's perpendicular right there. So this is the projection of u onto v. You see, here's the vector v, and this is the shadow that vector u would make onto v. So let's use projections to decompose a vector into components. So we're going to find the projection of vector u onto vector v, then write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So that's going to be w1, and then the other one is going to be w2. All right, you ready? So we just learned that the projection of u onto v, which is w1, is going to equal vector u dot vector v over the magnitude of vector v squared times vector v. Okay, so that's going to be 3 times 6 plus negative 5 times 2 over the square root of 36 plus 4 squared. That's the magnitude of v, 6 squared plus 2 squared. And then I'm going to take all of that and multiply it by vector v, 6 comma 2. Okay, so that's going to be 18 minus 10 over 40 times 6, 2, which is 8/40 or 1/5 times 6, 2. We're multiplying a vector by a scalar, so we just distribute the scalar, and we get that w1, vector w1, is 6/5 comma 2/5. Okay, so w2 is vector u minus vector w1. And vector u is 3, negative 5 minus vector w1. That's 6/5, 2/5. Get a common denominator. That's going to be 15/5 minus 6/5, comma, negative 25/5 minus 2/5, which equals 9/5, comma, negative 27/5. Okay, so the directions said write u as a sum of two orthogonal vectors. So that means that vector u is equal to W1 plus W2. And if you happen to add those together, you're going to get 15/5, which is 3. And 2 minus 27 is negative 25/5, which is negative 5. And that happens to be the same thing we started with.